Welcome back, All-Star Future Hall of Fame chemists. Today's video is going to serve as an introduction to periodic trends, which will be our topic of conversation over the next several days in class. In order to properly explain various periodic trends, namely atomic size, ionization energy, and electronegativity, we need to be able to discuss atomic structure and the forces that create the trend. So again, atomic structure, that term probably makes sense to you. But things like ionization energy and electronegativity, these are things that we will learn about in time. In this unit, we'll get to both of these trends. We reserve electronegativity for a future unit. You know, chemistry is the study of matter. It's the study of energy. And so today's video is really going to focus on the energy associated with forces, right? Really attractive forces, or perhaps at times even repulsive forces. Now, these properties, okay, that we're going to get into, these trends of the periodic table, rely on what we call the Coulombic attraction between the outer valence electrons and the nucleus, right? Obviously, we know that electrons are negative. The nucleus is comprised of both protons in addition to neutrons, which means that the nucleus, given that neutrons carry no charge, is going to be positively charged. And so between the nucleus and electrons, there's going to be this, attractive force that exists. You might be familiar with like the electromagnetic force, the electrostatic force. We are going to try to get that terminology down, referring to it as the Coulombic attractive force. Okay. When it comes to Coulomb's law, don't fret. I know there's an equation on the page with some variables we probably have not seen before. That being said, we are only going to use Coulomb's law in a qualitative way, not quantitative way. So we're not going to be putting in numbers and kind of plugging and chugging. We're just going to use it to describe, again, the magnitude of the force of attraction between oppositely charged particles. And so that's what Coulomb's law really does for us, right? It tells us that force of attraction. And we're told that it is directly proportional both to the magnitude of charges, where Q1 is normally representative of the positive charge in play, Q2 is representative of the negative charge, but it's also inversely proportional to the distance squared between those charges. Okay, so again, D is standing for distance. K is just a constant. In theory, we could eliminate the K and say that the force of attraction is proportional to Q1, Q2 over D squared. Okay, so we could get rid of that K by tying it up into that proportionality notation there. So to kind of break this down a little bit, I think this is going to make a lot of sense to you all. If the nucleus has a really large positive charge, right? If the magnitude of Q1 is really high, then obviously that numerator is going to have a large value, which results in the force being quite large, which is to say the force of attraction is large, and so electrons will be strongly attracted, right? That's what we are talking about right now, is how well electrons are being held onto by the nucleus, given that, again, electrons are negative, that nucleus is positive. Moreover, going back to this expression, electrons that are really close to the nucleus, these things are going to be very strongly attracted. So as this distance between electrons and the nucleus becomes diminished, as we have a smaller value in our denominator, this is going to result in a larger value for the force. Okay? So today's video, again, we're going to be focusing on the Coulombic kind of attraction. In the short term, we're really going to be keying in on this term right here, focusing on the Q1, okay, and what's going on with that positively charged nucleus. So that brings us to the concept of nuclear charge. So we're going to start by talking about kind of a basic definition for nuclear charge, and then we're going to get a little bit more specific and get into what it means to talk about the effective nuclear charge, or ZF. Okay, the nuclear charge, as far as the definition goes, is one of those things where you can almost just kind of use the words to define the term. Nuclear charge is really just the charge of the nucleus, and as we talked about earlier, given that neutrons are neutral, really we're just talking about the pure number, okay, of protons there. So, when we talk about, say, the second row on our periodic table, that second period, as we move from left to right on the periodic table, we find that in going from 3 protons up to 10 protons, obviously the nuclear charge is increasing, okay? And the way that we would actually talk about this, maybe we'll define this here, is that the nuclear charge is represented as Z, whereas the effective nuclear charge is again represented as ZF. So if we wanted to talk about nuclear charge right now, we wouldn't say 3 protons, we'd actually just say +3, +4, so on and so forth. That would be like its Z value, again, the charge of the nucleus, okay? So, again, as we move left to right on the periodic table, we're finding that nuclear charge is obviously increasing, okay? And as we move down the periodic table, so what I've tried to illustrate here is as we move down, say from lithium to sodium to potassium, if we happen to have a periodic table handy, so from lithium to sodium, potassium, obviously that nuclear charge is increasing as well. We go from +3 to +11 to +19. However, things are never quite that simple. Things are going to get a little bit more complicated, okay? So, and this is where the concept of effective nuclear charge comes into play. So let's take a look at lithium, okay? So for lithium, when I investigate kind of like this Bohr model for lithium, if it has 3 protons, we would say that the nuclear charge is +3. Again, that is like the kind of the nucleus's ability to attract electrons. We can kind of quantify that as like a +3 charge, right? The problem is that this electron right here, okay, though it is attracted to this positive nucleus, it's also being repelled by core electrons, okay? So this is going to bring us into this concept of effective nuclear charge. So as much as this electron right here is in fact being attracted to the positive nucleus, what about this electron? And what about this electron? These core electrons found in that first energy level actually have the capacity to repel that single valence electron. And so this decreases the nuclear attraction, okay? And so as far as that formal definition goes for effective nuclear charge, the amount of positive nuclear charge that is experienced by any individual electron is the effective nuclear charge. And so the difference really is how we go from nuclear charge to effective nuclear charge, given that at times, because of this repulsive effect we just got discussed, that nuclear charge can actually be diminished. So in the case of lithium, while you might think, oh, its nuclear charge is +3, because these core electrons have the ability to essentially diminish the nuclear charge, right, and repel out the valence electrons, the effective nuclear charge, it's almost like the nucleus is really only pulling with a force of +1.28, okay? So we can actually talk about this as far as like this ability of core electrons to repel valence electrons as far as shielding goes, okay? So that's the term that we attribute to this concept. So again, shielding is the name we're going to use for this reduction of the true nuclear charge, again represented by Z, to the effective nuclear charge. And this is the definition for shielding in a nutshell. It's that core electrons shield valence electrons. These core electrons literally, if we want to think of it as repelling, they repel the valence electrons, okay? That's what they do. So if we want to investigate, say, that first column, going back to lithium, sodium, potassium, let's take a look at kind of the snapshot here, okay? So what we find in going down that first column, the alkali metals, which we took a look at yesterday in class, as we go from lithium, sodium to potassium, what I've done is, given the number of protons, I've just kind of a quick, recall that the nuclear charge is going to be the same as the number of protons. So +3, +11, +19. But again, what's happening is that we have different numbers of core electrons as we go down the periodic table. So in all cases, there's only one valence electron, right? It's in that S subshell, okay? So this valence electron is like the 4s1, and this is the 3s1, and this is the 2s1. So as we go down, what we find is we have 2 core electrons for lithium, whereas we have 10 core electrons for sodium, and we have 18 core electrons for our potassium. So though the nuclear charge appears to be increasing by this, really significant amount, because we keep adding core electrons, because we keep adding, those inner electrons that are repelling the valence electrons, we find that the effective nuclear charge, it does increase, but not by this enormous amount, okay? So to recap that, while the nuclear charge, right, just the pure number of protons, is increasing significantly as we go down the periodic table, right? 3 to 11 to 19, because we are adding full energy levels worth of electrons, right? We're adding more and more and more core electrons. This increases that shielding effect, which again is the core electrons repelling the valence electrons. So when we say that the ZF, the effective nuclear charge, increases less so, what we really want to do is really say that ZF doesn't increase by a significant amount. So again, as we move down the periodic table, the ZF does not increase by a significant amount. It does, right? That's what these numbers suggest, okay? But once we get back to Coulomb's law towards the end of this video, we're gonna find that it's actually a different variable in that equation that's really going to dictate the force of attraction, okay? So if this is what's happening with shielding as we move down the periodic table, okay, so shielding definitely increases down the periodic table, okay? What happens as we work, say, across the periodic table? So let's take a look at these kind of two atoms. We'll go back to lithium, and then we're gonna take a look at fluorine. Okay, so the question at hand is, how does shielding work again across the periodic table, moving, say, again from lithium on the left, all the way over to fluorine there on the right? Well, investigating lithium, I find that I have one valence electron, right? And I have 2 core electrons. For fluorine, I have 7 valence electrons in that energy level, and I still just have 2 core electrons. So for both lithium and fluorine, like I said, only 2 core electrons had the ability to shield that outer valence shell, right? The outer energy level. Okay, so again, if we're doing a little record keeping, we have 2 core electrons and I have 1 valence electron. Over here for fluorine, I have my 2 core electrons and I have 7 valence electrons. Okay. As we move from left to right on the periodic table, and you think about kind of like building atoms, right? We're adding protons, we're adding neutrons, we're adding electrons. Well, those electrons are actually getting added to the exact same energy level, right? N in this case is 2 for both lithium and for fluorine, okay? And what we find is that valence electrons don't actually do a great job of shielding each other, okay? It's not like, these electrons are kind of literally pushing out on this electron, like that's occurring, right? Core electrons have the ability to repel valence electrons. But who's to say that this valence electron is really pushing out on another valence electron, okay? And we could get into that. In fact, valence electrons can shield each other a little bit, but that's a topic of conversation for a more advanced chemistry course. So for now, we're largely going to say the valence electrons just don't really do a great job shielding each other, okay? And so as we move left to right on the periodic table, our effective nuclear charge does in fact increase rather. And that's what we see with these numbers, right? So again, going back to like, okay, just the pure nuclear charge, right? Just the number of protons as we go from lithium all the way to say neon, +3 up to +10, great, okay? But again, there's some shielding, right? We do have those electrons, those 2 electrons in the 1s level there that have the ability, those core electrons, to repel the valence electrons. Okay, but clearly as we go from 1.28 on the left side, and we get all the way up to 5.76 as an effective nuclear charge. Again, that's the magnitude of that positive pull of the nucleus. Okay, so again, ZF does increase as we go left to right. Just as a quick reminder, like when we were looking at potassium just a moment ago, maybe I'll just redraw that really quick. Okay, so again, it went like on the left side of the periodic table going down, it went like lithium, and then we had, sodium with its just 11 protons. And then we had our potassium with the 19 protons. This is what our structure for potassium looked like, right? It had 4 energy levels worth of electrons. And we talked about just a moment ago how its nuclear charge was +19, but its effective nuclear charge was actually only +3.50. And so if you look at this, it's crazy to think this, but even though potassium has 19 protons, right? So you think, whoa, like really, really strong pull of the nucleus on its electrons? Not really, because of these 3 energy levels, right? 1, 2, 3 energy levels worth of core electrons that are literally repelling out, right, on that valence electron. it's really diminishing that nuclear charge to get to that really low kind of effective nuclear charge. In fact, even though neon has less protons, it actually has a greater effective nuclear charge because it experiences less shielding, okay? All right, so let's go ahead and kind of wrap all this up. So getting back to Coulomb's law, okay? Like we want to be able to use that equation to, again, qualitatively make sense of different phenomena, which again, we're going to get into things like size, ionization energy, electronegativity, okay? But just to kind of recap, whenever it is we're moving across the periodic table, okay, what we want to do is talk about effective nuclear charge. Okay, so again, K is a constant. We're never really going to worry about that, okay? As we move left to right on the periodic table, we're always going to be in the same energy level, right? When we go from, say just like magnesium, right? Its valence electrons are in the third energy level. Well, in going over to chlorine, its valence electrons are also in the third energy level. So while the size of atoms do differ, okay, and we're going to get into that again in the coming days, that's really not an important point as far as justifying trends across the periodic table. What we want to key in is this variable right here, okay? So as we move left to right on the periodic table, our effective nuclear charge increases. The magnitude, the literal value of Q1 is increasing. And if we have an increase in this value, we're going to have an increase in our numerator, which again results in a larger Coulombic attractive force. So as we move left to right on the periodic table, the effective nuclear charge increases, and subsequently, there is a greater force of attraction, we'll say between the nucleus and the electrons. And again, that's always the relationship that we're really going to be taking a look at as we get to these trends, like what's going on with the nucleus and the electrons, okay, namely the valence electrons. So again, whenever we're trying to justify, the only thing we need to concern ourselves with as we move across the periodic table is going to be the effective nuclear charge. As we move down, there's kind of two things we should consider, okay? The first is that as we move down the periodic table, the number of energy levels increases, right? We go from, say, 1 to 2 to 3, so on and so forth, okay? And the ramifications of this are kind of the following, right? Whenever we have that small value for n, right? So 1, 2, 3, principal quantum number there, like we have a really, really small distance in between the positive nucleus and the negative electrons in that valence shell, as opposed to, say, a larger value for n, where we see just kind of a crude sketch here, that distance has increased, okay? So in kind of explaining this, as we move down the periodic table, if n is increasing, as this distance increases, well, whenever we have a larger value in our denominator, that is going to result in a weaker, so we'll say results in a weaker force of attraction between the nucleus and the electrons. Okay, so again, with an increased distance, so as n becomes larger as we move down the periodic table, it's that increase in distance that's going to result in a weaker Coulombic attractive force between the nucleus and the electrons, right? It's almost like the concept of like, hey, if we have a north end of a magnet and a south end of a magnet, and we bring them in close proximity, like you can feel, right, that force of attraction. But as there's an increased distance between those two magnets, like that force, all of a sudden, that attraction becomes largely negligible, okay? The second consideration is that as we move down the periodic table, because we have increased shielding, this is going to result in that effective nuclear charge being held somewhat constant. Okay, now again, earlier we said that it does increase, but that increase is rather insignificant. Okay, so for all practical purposes, as we move down the periodic table, what we really need to focus on as far as our Coulomb's law equation goes is really nothing to do with charges. Okay, so we're going to kind of cross this out. We're not really going to concern ourselves with effective nuclear charge. What is really going to kind of, again, govern these trends, govern these properties, and tell us a lot about the energy associated with that force, the strength of that attractive force, is just going to be the distance. Okay, so again, when we move left to right on the periodic table, we do care about effective nuclear charge. When we move down a periodic table, it is the distance. It is how far away is that valence electron from the nucleus. That's really going to tell us a lot about that force of attraction. Okay, moving forward, we are going to use what we know about Coulomb's law, moving across and down, to explain the trends, again, of atomic size, ionization energy, and electronegativity. Thanks for tuning in, guys.